you're supposed to see COMSOL Multiphysics. Okay. So we're going to talk today about the part 2 of COMSOL Multiphysics, Introduction to COMSOL Multiphysics session. We're going to discuss the structure of the model, how can you build a model through the tools we have, meshing tools, solver settings, and all that stuff. So in the beginning, we had last week an introduction to COMSOL Multiphysics part 1. So let's summarize it. We have the ribbons on the top. Sorry, you have the tabs on the top. Each tab has its own ribbon. So when you open COMSOL the first time or any time, you get the new page, which you have model wizard or a blank model. You can start with either. So today we're going to start with a model wizard. We will start with a three-dimensional model. And then we can select our physics. So today I'm going to use structure mechanics. The example I'm working with is a bolt and a wrench. The wrench is applying a torsion on the bolt. So this is the simple model we're going to start with. We have another model also we can work with later. So this is the first one. So my first model is going to be structure mechanics, solid mechanics, and then I can click add. Next, I can click on study. Select my solver, either stationary or time dependent or any of these. So my model this time is just a stationary solver. Click done. As you can see, anything I select from the physics or the studies, I can get the description and a brief explanation about it on the right-hand side. Now I can have my interface. This is the ribbon for each and every tab. On the left-hand side, I have my model builder. In the middle, I have my settings window, and on the far right side, I have the graphics window. If we talk about the structure of any model in the COMSOL Multiphysics, we have first the name of the model, which is the root. Our model now is called untitled.mph. So if I save it as any model, let's say I would like to save it in my desktop, and my downloads, sorry, and then call it test1. So my model now at the root is called test1.mph, multiphysics file. If I go to my root, I can find a title for the presentation title and description, the name of the author, everything I can enter, and then I can extract a thumbnail from this results. If I have results at the end, I can extract a thumbnail to put it in this window. What this actually means is that when I use the results tool to export it as a Word file or extract it as a report file, all of these data, which is the author name, the date, the description, the title, and also the thumbnail, are going to be used in the cover page at the beginning. So let's start with the parameters. We have first the global definitions and then components. I can have in my model multiple components, and each component can include a 2D or a 3D or a one-dimensional, just a zero-dimensional system, if it's just an equation. So I can have multiple components. If you go to the global definitions, we have parameters and materials. The parameters we include here are going to be used in any other component in the whole system. So you can only have a single parameter for each and every parameter. A single name for each and every parameter. So if I have V1, I cannot repeat it as V1 and another V1. Each one has its own value. I can have only one V1 in my whole system, because this is a global definition and it acts for the whole system. It can be extracted or called for in the whole system. So we can have our parameter. Let's say my parameter today is force. Let's call it F1. The expression is going to be 150. And as we said last week, you can use square brackets to define your units. So I can either use Newton or any other unit to describe the force, and between square brackets is going to be converted automatically. A description is a way to keep an eye or um, keep yourself refreshed when you open the file later. If you have multiple parameters, you can know which parameter stands for what when you have it in the description. Also, the description is extracted also when you create a report file in Word as a Word text or text document. The parameters and the descriptions are extracted into the report file, so it's easier to understand this way. So these are my first description, my first parameters. Next, I'm going to go into the component one under geometry. For a first model, I can start with a simple geometry, which I'm going to import. It's ready made in the COMSOL file, so I can go to geometry here, either right click on it or go to geometry tab and click import. Under import, I can go to browse, select my drive C, program files, COMSOL 5.5, Multiphysics, and then go to applications. Next, I can go to COMSOL Multiphysics folder, and then structure mechanics. I have the wrench, three-dimensional geometry ready there. Import it. So this is how you import either COMSOL geometry files or any other supported geometry files or CAD files into COMSOL. As simple as that. So now I have my wrench ready-made with the bolt. What I need to do now is to define materials for the wrench and the bolt and apply the boundary conditions. In my case, which is either applied force on the far side, and a constraining boundary condition to constrain the whole system from just floating around, because now it's not bound to anything. What I'm going to do is to bind the back part of, or the back face of the bolt to an unmovable object or an anchor. In our case, the boundary condition is called fixed constraint. So if we follow the workflow here under the component one, you can see that if you can, after geometry, after you finish building your geometry or geometries, you can go to materials, either right click or click on material tab up there to find add material from library. I can go to my library. I have multiple materials there. I can have my wrench and my bolt in two different materials if I want to. So I can go for structure steel for the bolt. Or the wrench, in my case. The first material you select, it's automatically assigned for all domains. As you can see, the domains are 1 and 2, and they're automatically assigned under structure steel. If I select another material, so for example, if I select my titanium, it will not be assigned to anything. So I can then go into titanium, make sure the selection activation switch is on or green, and then select maybe my bolt or wrench. So in this case, I'm going to select my bolt. Now my bolt is titanium, while my wrench is steel. And since I've used domain number 2, which is the bolt in titanium, it's automatically overridden under the structure steel. So if I would like to define a certain material that's not available in the library, I can go to materials on the top here or right click here, and then go to blank material, enter my properties that I would like to define for such material, and then use it. Currently, I can use either the material or edit the properties here, as these are all editable. I can also insert a function, as I can use interpolation, whatever way you would like to describe your material property or any term in COMSOL, you can use it. You're not bound with just scalar values or numbers. You can use any other thing. So maybe I can tie the density or the Young's modulus to temperature or time of day or whatever. Any function you would like to use, you can use. Next, inside mechanics, which is my physics, I can go to physics under boundaries. I would like to have a fixed constraint boundary and a boundary load. So I can go to fixed constraint, rotate my model using the left mouse button, and then select the back side of the bolt. Now my bolt is fixed to this anchor, and then I can select a boundary condition from here, which is boundary load, boundary load, boundary load. The boundary load is going to be applied on the far end of the wrench. So this is my boundary load. I can use the tools here or the buttons here I have to adjust the geometry, so I can either zoom extend like this or go to default view, which is this isometric view. Under the boundary load, I can go to settings, select from the load type, total force, and then since I would like to apply downward pressure or downward force on it, it's going to be in the Z direction, negative Z direction. And in my case, it's F1, which is the parameter I created earlier, and now I can call on it from there. So next, I can go to mesh, select element size, use the physics control mesh this time, click finer, build all. And now I have my mesh. Last thing I can go there is to go to study, click compute. Since I don't have anything to do to change in my study settings, I can just click compute. When it's done, you can find the default plots under results, and then we can create our own plot. Depending on what kind of study you've used, depending on what kind of physics you've used, the plots come out based on that. So in my case, it's a stationary study, and I have only one physics, which is solid mechanics. So I'm going to get the von Mises stress plot, for example, and I can add more plots. I can have different types of plots. So I can slice into it. I can plot certain values at a certain point, extract data. For example, certain stresses at certain junctions in this area and this volume. So in this plot, we have the stress, and it's a solid volume of stress. As you can see, the displacement of this wrench is greatly exaggerated. You can go to surface deformation, and you can see it's multiplied by a value. I can also disable the deformation. So now I have my stress plot only. Let's say I would like to create a new result or a new plot. Let's go to results, 3D plot group, since I'm using a 3D geometry. I can use also the slice plot, which is going to create multiple slices across the volume as much as I want, or at a certain coordinate or coordinates I want, whatever. So I can click on slice. Whatever plot you select, or whatever plotting you select here, you can select the expression, what exactly are you plotting in this plot. So either type this syntax, which describes the displacement in this area, in this way, in this case, or since you're not supposed to memorize all the expressions, you can use the add expression tool, replace expression tool, sorry, and search here either by keyword or by going through the tree. So in my case, I can go to solid mechanics, stress, and I can go to whatever I want. I would like to solid Mises, which is von Mises stresses, or I can type here von, and I can find the same thing. Any keyword would suffice, and then select my units, whatever unit I have. So megapascal, which is mostly used, and I can click plot. By default, I get 5 surfaces or 5 slices across my volume. But I would like to change that. I would like a certain slice on the ZX plane. So I can go to ZX plane and at a certain coordinate, which is 0, 0. Plot. Okay, I get this slice throughout my wrench. I can also plot certain values across for example, the stress along the whole wrench thickness or at a certain level in detail, or if I want to, whatever kind of plot I would like, I can use. I can also, for example, use annotation to express either comments on my plots or extract certain values from the plots. So if I put an annotation, at the position of 0x and 0z, maybe 1y, 1 times 10, okay, 0.001y. Let's remove this slice first so I can see my annotation. So this is my annotation point, which is the black dot in the middle. I can either type text, so it's, for example, test here, and I can plot it as an annotation, or I can, for example, extract the data from a certain expression here. So I can go use this evaluation syntax like this. I can type eval and then open the expression, which I can't remember what's the expression. I can go here again, von Mises. So it's eval, open parenthesis, von Mises, close parenthesis, and then plot. Now this is the value of the stress in this area or in this part of the system. So now I can use my slice again or my volume, plot the stresses, and annotate a part of it using the annotation tool like this. I can also change the colors from the settings for anything. So in the here, I can change the color to white, which is more visible. I can change only the color table for whatever plot I have using the coloring and style. So for example, I can use thermal, which is white to dark red, or I can use traffic, which is red, green, and blue, red, green, and yellow, and so on. So lots of tools and lots of flexibility in this area. Before we start with our next example, please, if you have any questions, please either raise your hand or use the chat box. Okay, so let's continue. My next example is going to be a thermal expansion on a just a certain member or a certain steel member or a steel element. It's a very simple model. What we're going to do first is to draw my geometry, apply my physics, and then find the results. I can either find as a stationary study or a time-dependent study, whatever I want. So in my case, let's start. Go to new, open a new model wizard. Let's have it as a 3D model. In my 3D model, I'm going to use the heat transfer part. I think it's in structural mechanics. Yes, thermostresses is in structural mechanics. I'm going to use the multiphysics, which is already implemented in COMSOL. So when I use the multiphysics, for example, thermal stresses in solids, you can find the description of this multiphysics. If I click add, it is going to automatically add the heat transfer part of the physics, the structural mechanics part of the physics, and the multiphysics that combines them together. Yes. So the solid mechanics is added, the heat transfer in solid is added, and then the thermal expansion multiphysics node is added automatically. Next, for study, I can have time-dependent solver or a stationary solver. Let's go for time-dependent solver. So for my model, I can either start with the geometry. So if we go to geometry, I can draw a rod, either a cylindric rod or a square cross section rod. So if I select block, I can also change the units I by default is used from here. So geometry, instead of meter, I can have it in centimeter. So let's go to block. It's 1 by 1 by 1 by default. So let's say it's 10. It's 1 by width, and the depth is going. The height is going to be. So yeah, its width is 10. Let's try this way. Yeah, this is what I want. So we have this steel member, or we're going to define it as steel later. This geometric member. We're going to apply a boundary condition for a heat from one part and see how the heat transfers throughout the whole body. And also we can see what kind of thermal expansion or deformation happens to the body. For us to do so, there are multiple things to consider. First, we need to affix this body to a certain anchor or a certain reference point, either a floor or a wall or anything. So let's start by first going to materials, right click on materials, add material from library. Let's say it's going to be made out of copper. So this is my rod made out of copper. Nothing special about it. I can also add another part to this rod. Let's say I would like to have a curved surface here. Let's see if I can create a U-shaped bend at the end of this block. So I'm trying to challenge myself. So let's go to revolve. Select my face. No, this is the wrong axis. So the axis of revolution is going to be 0 in X, 0 in Y. The axis of rotation is going to be 10 the X direction, like this, and not 360 degrees. Let's make it only 180 degrees. So yeah, something like that. You can also have the axis a little bit further away in the negative Z direction. So it's, for example, -5. Yeah, we're going to have something like this. Too much. Let's make it -2. Yeah. So this is the U-shaped bend I try to use. So as you can see, there's lots of tools you can find in this geometry ribbon. You can find lots of tools which you can create your own geometry. It's like bits and pieces, just combining bits and pieces, welding parts together, subtracting other parts from each other, and then you have this at the end. I can also create a union out of them. So I'm welding them together to be a single domain. I can go to union, select my first. Oh, yeah, it's a single domain by default. I didn't create a two-domain system, just single domain. So yep, now we have our copper domain like this. I'd like to split them together. So partition domain, also another tool. So I can partition the domain. The work plane. Yeah, the work plane is going to be, we can create a work plane to partition at. Is going to be ZX work plane. No, ZY work plane at X equal 10. Yeah, this is my work plane. I can go to partition domains and select the work plane, which is WP1. Yeah, this one. Yep. Now I have two domains. If I go to copper, I have to select two domains to make sure I have selected them all. Let's say they're all made of copper in the solid mechanics, or them are selected. I can then go to physics, boundary conditions, then affix my bottom part here to affix constraint. And then I can go to heat transfer. Now my whole system is just fixed to this wall from this side. I can also fix it from the other side here to a wall, and if it expands, it's going to go in the ZX direction, sort of more or less in the right-hand side. And also I can also use another boundary condition, which is, for example, roller. Roller allows to movement in a single plane, but not the other. So I can have it, if I use a roller condition on this face, it can move in the Z and the X direction, but not in the Y direction. So let's assume that you have a roller. No, it's on the solid mechanics, boundary conditions, roller. I can apply a roller here. So now it cannot move anywhere from this area, but it can move around on this along this plane, which is the ZY plane for this face or for this area. As for the heat transfer, I can apply a heat flux. For example, from these 4 sides, and since, or 5 sides, and since it's metallic, made of copper, it's going to be conducting throughout the whole system and then expanding later. My heat flux is going to be, for example, 200 watts. Too much. Not say 200 watts. And since we have a time-dependent solver, we can go to the, sorry, let's go first for meshing. I sort of skipped through a meshing. Let's mesh this domain. We can either use the default mesh, like build all, and this is what we get, or we can use our own optimized mesh. So I can go to mesh, select a boundary. So for example, select a function, which is, for example, swept mesh. Select the domain. I would like to just sweep through this domain. I select my source face, which is this face, and then select my destination face, which is, it's hidden here, so I can just unhide it or look through it by using transparency function. If I hover over this face, I would like to select the next face or the face behind it. I can use the scroll. Now I've selected the other face, so this is my other face. And then sweeping method, I can use quadrilateral, for example. Now I have my quadrilateral mesh. Let's first use another boundary condition called map mesh. Move it before the swept here. I can use the map mesh on this face. Nope. Oh, no, this is not what I wanted. Sorry. Yeah, free quad. Let's free quad this face first, and create a size node for this specific free quad generator, and then go for a different size like this, or even finer, extra fine, extremely fine, yeah. And then sweep through it the whole volume. So we have this extremely fine or less mesh for this domain only. And then we can create another mesh for the next domain. For example, the next domain, it can be a free tetrahedral for this domain only, or the remaining domains. You can either use both functions and then build. You can also use a specific size for this mesh, for example, finer. Or I can use custom and specify the maximum element size, minimum element size, and so on. These are 2 ways to define my mesh size and mesh type. Next, I can go to time-dependent solver. My range is just 1 second from 0 to 1 by using 0.1 second as a step. I can use this tool as a called range to define my steps or my whole range. For example, from 1 to 2 seconds, and the step is going to be 0.1. Yeah, let's make it 0.2, and then replace. Now I assume I can run my model. Let's see if I missed something. It can take some time on my computer to solve a time-dependent solver, a time-dependent model. It can take less time on your computer if you have a much powerful computer than mine, but it should be solved in less than a minute for this simple model at least. Okay, so the stresses, you can see the stresses are increasing, but as you can see, it doesn't look like it or doesn't appear that explicit on the graph because the legend or the range of the numbers, the range of stress is changing along the time. So let's start with defining or working with the range of this plot. Let's go to stress plot, surface. You have this range which is just moving around. We can fix it. So my minimum color range is this, and the maximum color range is going to be like this, 4 million Newton per meter square. Okay, plot. So if you look at this, there's also deformation happening here. So my model is just heating up and stresses are increasing, and also it's just moving on this ZY plane. If you go to temperature plot, you can see also the temperature which is increasing over time, as you can see in the legend. So we can also do the same thing with the range, fix the range from the default one to maximum, which would be maximum is 306. Okay, so my here 300 no, this is minimum range. My maximum range is going to be, for example, 310 Kelvin, 310 Kelvin. Plot. So first thing, it's very cold, so it's red, as this legend said, and it starts heating up. You can see heat starts from this area, which is the heat flux boundary condition, and dissipates throughout the model until it starts heating up the rest of the U-shaped band. We can increase the time domain or increase the power of the heater or heat flux boundary, and we can also increase the calculation time domain, but it should take more time in calculating that. So